Once again, I welcome in the course of Foundation Engineering. So today I will discuss the new module, that is Machine Foundation. In Machine Foundation, firstly I will discuss the various types of machine, and then types of machine foundation, and then basic definition used in the machine foundation, and after that design criteria of the machine foundation. And after that I will discuss the mass spring model and then mass spring dashpot model with two separate cases: mass spring model with free vibration cases, then mass spring model with forced vibration case. And after that I will discuss the mass spring dashpot model with free vibration, and then mass spring dashpot model with forced vibration. So let us discuss about the machine foundation. So machine foundation, we can in foundation engineering we have already discussed about the static load. So in machine foundation mainly I will discuss about the dynamic loads, and these dynamic loads may be due to the vibratory motion of the machine, movement of vehicle, earthquake, wind force, wave force, nuclear blast, mine explosion, or pile driving. So the dynamic loads transmitted to the foundation and their effects on the strata. So various types of machine I will discuss. So there are three types of machine, like reciprocating machine, impact machine, and high speed machine. So what is reciprocating machine? So reciprocating machine produce a periodic unbalanced force, and the best example of reciprocating machine like reciprocating engine and compressor. And such type of machine have the operating frequency is less than 600 rpm. For analysis, unbalanced force can be considered as a sinusoidal. Similarly, the second type of machine, that is impact type machine, and in this type of machine produces impact loads such as forge hammer and punch presses. Dynamic force attains a peak value in a very short time and thus dies out gradually. And in such type of machine have operating frequency lies between 60 to 150 blows per minute. And the third type of machine, that is a rotating machine or high speed machine, and such type of machine have operating frequencies greater than 3000 rpm, or generally we can say that the range is 3000 to 10000 rpm. And speed of such type of machine is very high, and the best example of this rotating type of machine like turbine and rotary compressor. After that I am going to discuss the different types of machine foundation. So there are generally mainly four types of machine foundation. The first one is block type. So in block type there is a pedestal whose weight is very high, and due to the high weight of this pedestal, their natural frequency is very less, as we know that the natural frequency is inversely proportional to the mass. So this type of machine foundation consists of a pedestal resting on the footing, and this is the machine. So foundation has large mass, and due to this large mass, small natural frequency will occur. Second type of machine foundation, that is box type, and it is also called the caisson type machine foundation. Foundation consists of a hollow concrete block. We can see that this is the hollow concrete block, and the mass of the foundation is less than that in the block type, and natural frequency is much higher as compared to the block type. So the third type of machine foundation, that is wall type. So there are wall type of foundation consists of a pair of walls having a top slab, and machine is placed on the top of the rest on the top of slab. So here we can see that this is the wall and this is base slab, and this is the machine. So this is the third type of machine foundation, and the last one is that is called frame type machine foundation. So this type of machine foundation is generally used for high speed machine. So this type of foundation consists of vertical columns with having a horizontal frame at their top, and the machine is supported on the frame, and this type of foundation is generally used for high speed machine. The basic definition that is I am going to discuss, that is very important for the machine foundation, like what is vibration, frequency, amplitude, free vibration, forced vibration, what is resonance, what is frequency ratio. So vibration is the time dependent repeated motion of translational or rotational time. Similarly, frequency, so the number of cycles of motion in a unit of time expressed in hertz or cycle per second, or circular frequency is generally expressed in radian per second. Similarly, amplitude is the maximum displacement of a vibrating body from its mean position. Free vibration. So generally in free vibration, our external force in the body will be zero, and vibration of a system when it is displaced from its equilibrium position and left force to vibrate. And the external force is zero in free vibration case, and external force will exist in case of forced vibration. Similarly, the natural frequency, so the frequency at which a system vibrates under the effect of force inherent to the in the system. Similarly, operating frequency, so the frequency at which a machine is operating, and the resonant frequency, so the frequency at which the maximum response occurs in a system subjected to a steady state forced vibration. And the ratio of operating frequency to natural frequency is called frequency ratio. And the another definition, that is resonance. So when the frequency of the exciting force or operating frequency equals to the natural frequency of the foundation soil system, or we can say that at resonance our frequency ratio value will be unity. So at resonance the amplitude of a vibrating system is maximum. Similarly, the another term, that is damping. So the resistance to motion which develops due to friction and other cause is known as damping. And according to D'Alembert principle, the force due to the damping constant, that is F is equal to C into Z dot, where F is the force, C is the damping constant, and Z bar is the velocity, or we can write dz by dt. Degree of freedom we have already seen in the structure analysis. So the number of independent coordinates required to describe the motion of a system. So here we can see that for this mass spring dashpot model, there is a one the degree of freedom for the system is 1. Here we can see that two springs attached with two mass systems. So here the degree of freedom is 2. A rigid block foundation has 6 degrees of freedom. Translation along x, y, and z direction, and rotation along x, y, and z axis. Here we have seen the x, y, and z axis are called respectively pitching, rocking, and yawing axis. So the general design criteria of the machine foundation. So a good machine foundation should satisfy the following. So we have already discussed the design criteria for the machine foundation engineering. Means it should be safe against shear, and the settlement of the footing should be within the permissible limit. So here that is also valid for the machine foundation also. Like ordinary foundation, it should be safe against shear failure, and foundation should not settle more than a certain permissible value. And for the machine foundation, there should be no possibility of resonance. Means frequency ratio should not be equal to unity, or we can say that operating frequency should not be equal to the natural frequency of the system. So either natural frequency is greater than the operating frequency, or natural frequency is less than operating frequency. So here there should be no possibility of resonance. The natural frequency of the foundation should be either greater or smaller than the operating frequency of the machine. The amplitude of vibration under the operating frequency of the machine should be within permissible limit. So there is a limit of the amplitude, and the combined center of gravity of the machine and the foundation should be on the vertical line passing through the center of gravity of the base plane. And the vibration induced should neither be annoying to the person nor detrimental to the other structure. So Richard has given the a plot for vertical vibration, which is generally taken as a guide for various limits of frequency and amplitude. So this is the Richard charts. Here on the y-axis we can see that the amplitude of vibration in mm, and on the x-axis this is the frequency in rpm. So here the various line we can see that not here we can see that noticeable to the person, and barely noticeable to the person, and here we can see that severe to the person. So these are the various ranges of frequency and amplitude. With the help of this chart we can use the various value, or we can read the various value of amplitude with different frequency value. And the another criteria of the machine foundation, that is the depth of the groundwater table should be at least 1/4 of the width of the foundation below the base plane. So now I am going to discuss the four cases. The first one is free vibration, and the second one is forced vibration. So as I discuss what is free vibration, so external force is zero. In free vibration, I will discuss undamped case, undamped and damped case. Similarly, in forced vibration, I will discuss undamped case and damped case. In undamped case, free vibration, I will discuss the mass spring model, and similarly here mass spring dashpot model. Means in these two cases our external force will be zero, mass spring model or mass spring dashpot model. Similarly here mass spring model, and in damped case mass spring dashpot model. So let us discuss one by one. Firstly, I will discuss the free vibration. So free vibration means external force is equal to zero. And in free vibration, firstly I will discuss the undamped case. Undamped case means will be no any damping. So our damping constant is zero in this case. Mass spring model. So if I make the mass spring model, let us assume this is mass and this is the spring. It's the displacement Z. So we can here a few symbol I am going to write here. M is the mass, Z is the displacement, Z dot is the velocity, Z double dot is the acceleration. So here according to D'Alembert principle, D'Alembert principle, we can write. So according to D'Alembert principle, we can write m into mass into acceleration plus spring force, that is k into z, is equal to 0. Or we can write z double dot plus k by m into z is equal to 0. So the solution of this equation, solution of equation first can be written as z is equal to a sine omega nt plus b cos omega nt. Solution can also be written as z is equal to a sine omega nt plus alpha, where a and b are arbitrary constant. A and alpha is also constant. Omega n is the natural frequency in radian per second. So we can write. So if I derive the first derivative of this z can be written as z dot is equal to minus a cos omega nt plus alpha into omega n. Similarly, the second derivative can be written as, sorry, it will be plus minus a sine omega nt plus alpha into omega n square. So if I put the value of the acceleration and the value of z in equation, in this equation, so we can write mz double dot plus k into z is equal to 0. So m into minus a omega n square sine omega n t plus alpha plus k into a sine omega n t plus alpha is equal to 0. So if I solve this, so it will be a cancel, sine omega n t plus alpha is cancel, so it will be m into omega n square is equal to k. So we can write omega n square is equal to k by m. So omega n is equal to square root of k by m. So this omega n is the natural circular frequency, where omega n is the natural circular frequency in radian per second. So here k is the spring stiffness and m is the mass of rigid body. So we can write let Fn be the natural frequency in cycle per second. So we can write Fn is equal to omega n by 2 pi. So we can write 1 by 2 pi square root of k by m. Similarly, let t be the time period. So t can be written as 2 pi by omega. So we can write 2 pi by omega. So omega can be written as k by m. So we can write 2 pi into m by k. Or we can also write t is equal to 1 by Fn. So in the next class, I will discuss the second case of free vibration, that is mass spring dashpot model, and after that I will discuss the forced vibration, and in forced vibration I will discuss the mass spring model and then mass spring dashpot model.